Okay. So, welcome to the Pezal Gürsey Center Higher Structure Seminars. Today, our speaker is Özgün Ünlü from Bilkent University. He's also my PhD supervisor, and today he will give us talk about infinite operas as simplicial lists. So, thank you, madam. It's all yours.
Okay, thank you for the invitation. So let me share my screen first. Yes, so today what I will talk about is joint work with Reddy Haderi. Here, that. Okay, so the goal is to give a model for infinity operads. So you might say there are many models for infinity operads, but well, we had several questions in mind that we wanted the answer. So let me first mention these questions. Okay, so but before saying anything else, let me just say operads here will be colored operads and non-symmetric. Okay, so what were the questions we had in mind? Well, first of all, working with operads, many authors use trees. So working with operads, many authors use trees. The question is, can we get rid of trees? Because the thing is, the definition of trees is pretty painful. And when you want to write everything in terms of trees, the definitions get very complex. So one thing we had in mind is, can we do everything using simplicial notions? So can we use only simplicial notions? Of course, there are examples where simplicial notions are used, but we had another question in mind. So we wanted to find a model for infinity operads whose relation to categories and quasis operads is similar. So want a model so that infinity operads has relation to operads similar to relation between quasi categories and categories. Let me just move this. Sorry. Yes. Okay, so here, let's remember the picture. So we have this simplex category to category of small categories. So we have this inclusion, which sends n to delta n. So here, this I will consider as ordered sets, and this I will consider as just the category associated with this ordered set. And cat is enriched in sets. So we could do the Unity extension and get this picture, delta to cat, and then a set. And then we have the nerve and the fundamental category functors. Now here, just to remember, the nerve of a category will be just functors from delta n to c in this unit extension. Now, let's discuss this case for categories just a little bit more. So here, let's say we have a category. Assume C is a category. And as objects A, B, C, and morphisms A to a morphism from A to B and a morphism from B to C. Okay, then in the two simplexes of this nerve, we have this functor x from delta 2 to C by sending 0 to A, 1 to B, 2 to C, and then the morphism from 0, 1 to F, and the morphism from 1 to 2 to G. So we depict this by a picture like this. So we write A here, and then we put a point F, and then we write B. We have G and C. So this is how we depict a functor from delta 2 to C in a picture. Now, let's discuss the, for example, face maps. So in NC1, the one simplices, we have GBC. So this is like D0, right? I mean, this is a functor from delta 2 to C. So the face maps send this two simplex to one simplex. D1 sends to G composition F, and D2 sends this to A, F, B. So it forgets G. Now, can we do something similar for operads? Okay, so let's say we have operad P with colors and this colors, let's say A, B1, B2, C1, C2, C3, and D. And then let's say I have an operation from A to C1, and then maybe from empty list to C2, and then maybe from B, B1 to C3, and let's say an operation from C1, C2, C3 to D. So these are like some operations in the operads. How do we depict this? So this gives us some two simplex. So two simplex. So here I will depict this two simplex by this picture. So I have B1, B2 coming into H, giving us a C2, C3, and then here I have C2, here I have C1, and then they all go into K, and they come out D. So this operator has a unary operation, a nullary operation, a binary operation, and ternary operation. Now the problem is if you want to repeat the same thing. So remember here we had a 2 simplex and we send it to 1 simplices. Now let's try to do the same thing. Now D0 will send this 2 simplex to this 1 simplex. Right. D1 will send this 2 simplex to this 1 simplex, where I have A, B1, B2, D, where here I have the composition. So F, G, H. Sorry, here I have K. Now the problem starts with D2. Yes,
K
so
in the other one.
sorry?
The first one is also K.
Oh, yes, thank you. That's right.
Just to, yeah.
Right. Thank you. Right, so now what are we going to do, right? So here, this is not just one simplex, but it's like a list of simplices. So it's like you have A, F, C1, and then you have G, C2, and I have H, B1, B2, C3. So the point is that can we replace sets? So here the point was N was going to a set, and now the problem is D2 is not a function. But we can find a category where this makes sense. So the goal is to replace set with a category which allows multi-valued functions. Or lists. So now a notation. So we will write, so for X, a set, for X, Lx will denote the set of all finite sequences in X. So it's the disjoint union of Xn. So it's the finite sequences in X. And we will define the list category as the category whose objects are sets A, B, C, and the morphisms from A to B are just functions from A to LB. So functions from A to lists in B. Now you can think, if you want, you can think of this as the Kleisli category for the monads. So L actually defines a monad from set to set, and you can think of list as the Kleisli category.
Is it rel relations?
It's not really relations because there's only one. I mean, see, I have L on one side. So I'm not,
No, I mean,
okay, so
this
things
monad
here,
is it power
like,
set monad or something?
sorry?
This monad L.
Is it
Uh,
Free
It looks
monoid
like
monad again.
which
So if you think of the adjunction with monoids by the free forgetful adjunction, it induces a monad on sets. Free monoid monad.
okay.
That's
So
that's
you
it.
can think of this also as free monoids. Yes. So here the list. I mean, it's categorical equivalence. Okay, now, so now, how can we define a nerve functor? So now we need to express this as some so here let's remember this. This was the depiction of some functor like this, right? Now we want to get something very similar. So we want to replace P here, and we want this depiction to be some morphism from something. So what should we put instead of this delta 2? Well, we will put objects called T alphas but before discussing T alphas, let me introduce a few more notations. So here, this will be the augmented simplicial category. So it's just a delta union an initial object. And the notation, let me develop one notation. Let's say I have an element in an n simplex in the nerve of this category. Then let's say alpha sends n to this augmented simplicial complex. Then for alpha, we will use A0. So A0 is where 0 goes, A1, 1 goes to A1, and then n goes to an. And the alpha is depicted, we will depict alpha by this sequence of functions. So when I say alpha, I will be able to use this notation from now on. It will just mean the image of alpha. And another definition is we will call alpha rooted if and only if an is the 0. So in delta plus, there is 0 here. And if an is equivalent to 0, then we will say alpha is rooted.
I guess there is a question.
There's a question?
Yeah, I had a question. What is delta plus?
Oh, it's just delta, and then you add the empty sets as well. So you can think of delta as ordered finite sets, which contains at least one element, and you just add empty set to this.
Delta consists of finite sets.
Yes, finite ordered sets. Mm-hmm.
Okay.
And you add empty set to it. So it's
Okay.
it has an initial object.
Okay, thank you very much.
Mm-hmm. Yeah. Okay, now another notation. So what's first of all, another definition. function. So a multigraph M is a functor M from delta op 1 to lists. So here I'm just restricting simplex category to objects which are less than 1, and I'm taking a functor to list, and we will call this a multigraph. Now,
Sorry, Özgün. There's also the being operatic condition, which I guess you can write down explicitly.
thank you. That's right.
Yeah.
Okay, sorry. Right. So the point here is I have M0 D0, sorry, M1 D0, S0 D1, M1 M0, and then the point here is that D0 S0 are functions, and only D1 is a listing. Okay. Should this part. Okay, then we will have this category of multigraphs. And we will have the adjunction, free and forgetful adjunction from multigraphs to operads. So you will just take M0 as colors and 1 as operads. You will freely generate an operad, and then when you forget the operatic structure, you will get a multigraph. And this way, we will define, okay, a tree. First of all, let me say M alpha is just the multigraph so here alpha, let's say, is a and simplex and rooted. Remember what was rooted? Alpha is called rooted if an is 0. So here, let's say we have a rooted alpha, then M alpha will be just sending 0 to all these colors and 1 to these operads. So I will not write down the exact definition, but you could guess what multigraph corresponds to an alpha like this. And this way we will define T alpha as the free functor applied on this multigraph. Okay, and then we will define the list nerve of an operad as this joint union of n delta plus rooted n of T alpha to P. Okay, so for example, if you remember this operad that we had, the depicted operad, these two simplex, I should say. Now, we will, so which tree, so what is the alpha? So we want to see this as some morphism from T alpha to some so we want to see this as an element in T alpha P. So P is as in the example that we discussed. So which alpha corresponds to this? Well, it will be alpha from T2 delta plus, which sends 0 to 2, 1 to 2, and 2 to 0. And now you send here in the this is the, okay, maybe I should say what does 0, 1 do? So the functor from 0 to 1 sends 2 to 2 by sending, okay, 0 to 0, and then 1 to 2, and 2 to, sorry, I shouldn't, that's the second. Right, 2 to 2. So it's just saying here so I have 2 to A, B1, B2. So these are some so the elements in 2 are colors in T alpha. And here, 0, the color 0 goes to A, color 1 goes to B1, and color 2 goes to B2. And then in the second part, 0 goes to C1, 1 goes to C2, 2 goes to C3. And then last part, 0 goes to D. So I'm talking about the morphism between the operad T alpha and P. In T alpha, I have all the colors in 0, 2, and 2 as disjoint union. So this 0 is different than this 0 because this 0 is in this 2 and this 0 is in this 2. So this color goes to this color goes to this color. So this is how the colors go. And now here, for example, alpha sends 0, 1 to 2, 2 like this. So it sends A to C1 because here A goes to C1, and then 1 goes to 2, 2 goes to 2. So both B1 and B2 go to C3. So this is how you see, so this is in N delta plus 2 rooted. So this is what this list nerve means. So you take alphas and simplices in the nerve of this augmented simplicial category that are rooted. Now you look at operad morphisms from T alpha to P for n simplices. So this is an example of a two simplex. So this gives us some cool faithful functor from operads to S list. Oh, by the way, maybe I should say, so S list is category of simplicial lists, but you take only functions as components for natural transformation. So maybe let me write that down. So let's say S tilde S list is category of simplicial. So it's just the usual functor category from delta up to list. And S list is full subcategory of this category where you only take functions as so you only allow, so the morphisms, sorry, no, I shouldn't say full subcategory, it's wide subcategory. Wide subcategory of S list delta, where you take all the objects are same, but the morphisms between two simplicial lists is only the morphisms in S list where natural components are, so morphisms from A to B in S list delta, where components of natural transformations are functions. So they're not listings. Okay. And then we have S list op, where this is the full subcategory of S list, where we only take operatic simplicial lists. As objects. So what does operatic simplicial list mean? It just means and so all face and degeneracy maps are functions except possibly dn. So it's just like what we had over here. So the only problem appears the multi-valued function. So basically, that's just what operatic list means. It's just a simplicial list where you have only the dn as a listing. So well, let me write more clear definition. So if, let's say, you have a simplicial list, we call this operatic if for every theta from k to n in, okay, if theta k is n, then theta star from xn to xk is a function. So if you hit the last vertex. So here, let me quickly remind you this thing over here. So D0 was what? D0 was D0 here I have so D0 is induced by 1 to 2, which sends 0 to 1, 1 to 2. D1 is induced by the map that sends 1 to 2, so 0 to 0 and 1 to 2. So as you can see, both of these hit 2. So 1 hits 2, 1 hits 2. Only in D2. So when you consider D2, 0, 1 goes to 0, 1, right? So you don't hit 2. And only this kind of things can be listings. That's the idea. So if k goes to n, then it should be a function. Okay, now the point is we want to have so one of the questions we had in mind, remember, is to have a relation between quasi-operads and operads relations. It's similar to quasi-categories and categories. So for this, let's talk about this junction between monodial categories and operads. So okay, now, so here I have, so given a operad, I can obtain a monodial category by just sending colors to the L of colors. And you could guess how the morphisms should go because it's just sequences of colors to sequences of colors given by sequences of operations. So L goes from operads to monodial categories, and this functor will be given by, so let's say V is a monodial category, then we define this operad with colors given by objects of V, and operations are just, so you put objects as colors. So it's just a morphism from A1 tensor all the way up to AN to B. So an operation from this sequence of colors to this color will be just a morphism from this tensor product to B. So this is just a morphism in V. And now you're defining an operation in this operad. Now, if you forget the monoidal structure that we have over here, then we basically get functor from operads to categories. And we had this list nerve to S list, and we have this nerve that the first nerve we talked about at the very beginning of our talk. And we have L coming from the, so remember, list was the Kleistli category of set. So there's this adjunction between list and set. This, so it induces this L. So you simplicially induce L. Now this commutes. The proof I will not talk about, but here the theorem that we have is the nerve theorem. So this will give us an idea about how to define the quasi-categories, quasi-operads. Now let X be a simplicial list. Then, well, there exists an operad P such that X is isomorphic to the list nerve of this operad P if and only if X is operatic and there exists a category C such that this Lx, which is now a simplicial set, is isomorphic to the nerve of this category. So this is pretty similar to what you have in categories. Well, it's just you can think of categories to a set. This is fully faithful, and a simplicial set is hit by a category if it satisfies a certain condition, like unique extensions of these ith horns, certain horns. So this you can compare now to that result. So a simplicial list is a nerve of operad if and only if it satisfies certain conditions. Well, here, let me not going to discuss the full proof, but just the implication in this direction. So the other direction is pretty clear, but this direction maybe needs some explanation. So here, given X, which satisfies the conditions, how do you define P? Well, you take the colors of P will be given by X0, operations in P will be given by X1. And now let's say we have two operations, A11 to AN1. So let's say I have F, F2, AK1, AK, and K to B1, BK, let's say. Let's say this is some element in LX1. So this is a list in Lx1, and let's say I have this G, B1 to Bk. This is another element in Lx1. Now, since Lx is a category, so I'm trying to prove this implication. So I assumed Lx is nerve of a category. So there's a unique extension of so there exists this unique extension H in Lx1, right? So this is a 2 simplex in Lx2. Now this is equivalent to Lx2. Now the point here is, okay, H is in Lx1, but C is rooted. So this is basically in X1. So what we did is we defined composition of operations. So because composition of operations in an operad looks like this. You take a sequence of operations, you compose with this, and basically now we have an element in X1, which is an operation. Okay, so because so rooted implies it's an X1. Okay, yes. Okay, and then now we want to have a similar picture to this. Okay, so remember we have this picture for categories and simplicial sets. Now, can we get a, so we started thinking about, can we get a similar picture for operads lists? Well, we wanted to have limits and colimits first. Well, for a while, we weren't able to understand these colimits limits very well. But then one day, Reddy came and said, he noticed that this S list op is actually a pre-sheaf category. So it solved all our problems because then you have all these limits and colimits. So now let me start mentioning that part of the story. Now, so the theorem is that, so there is a full subcategory F of S list such that this S list is equivalent to this pre-sheaf category. So now the corollary is that S list is complete and co-complete. And similarly, this S, so there exists some category gamma where I have S list op also category is a pre-sheaf category. And it is, and this category has a very nice structure. The objects are very explicit. So here the objects are just these rooted simplices, and morphisms from beta to alpha are just pairs, this form, theta k to n, and a in a theta k. So remember, I'm using this notation a theta k, which means just the image of k under this.
Sorry, such that beta is the restriction.
Oh, yes, sorry.
Yeah.
That's right. That's right. That's right. Theta star alpha a. Okay, but I mean, what I'm trying to say is that the morphisms here has a very explicit combinatorial description. So then we have this similar picture for this nerve. Where alpha goes to T alpha. Again, you can think of this as the Ionede extension, and we construct the U alpha here, which under T1 goes to T alpha. Okay, so now from here, it is possible to describe, oh, by the way, how much time I have?
Oh, it is 6:50.
10 more minutes.
10 more minutes, okay, thank you.
10 more minutes.
Okay, so now we want to understand the tick version of this. So define U alpha from delta to S, the operatic simplicial list by sending M to this U alpha M, where this is a simplicial list whose Kate simplices are theta delta K to this big N M A theta K.
I
And
know you
now
were in a rush, but that's delta up. It's sort of important.
oh, yes, thank you.
No, delta up. Yeah. Okay.
So, yeah. So this gives, so now we can give from delta up to operads by sending, by saying this V alpha is T1 U alpha. And in fact, this thing is in operads enriched in simplicial sets. So here we get a simplicial operad, which is in operads enriched in simplicial sets. And so now we have a very similar picture. Well, this is the homotopic coherent nerve. We send here alpha to this V alpha. And we again do unit extension. This gives this commutative diagram. So this is the picture that we had previously. And now here, we can now define quasi-operads as just like simplicial sets. So how was quasi-operads defined. So you had this picture. Okay, I guess I missed it. Okay, so in the previous case, we had S set to cat. Cat was faithfully living in S set, and the image was given by, so something is in the image if a certain condition is satisfied. So now, if you weaken that condition, the unique extension of warrants to just extensions, then you get quasi-categories. So we can do the same thing for operads now. So let X be a operatic simplicial list. Then we say X is a quasi-operad if this LX is a quasi-category. So remember this nerve theorem, which said X is nerve of some operad if and only if this LX is a category. So now we're just weakening the condition on LX and saying this LX is a quasi-category. Okay, maybe in the remaining 4 minutes, let me very quickly say a few words about homology. So here, you could easily get a functor from lists to abelian groups by sending a list to, so a list is just a set, so you can take the free abelian group generated by this set, and given any listing, you send it to this group homomorphism from the free abelian group on X to the free abelian group on Y, sending A to just summation I from 1 up to number of elements in the list, UAI, where UA is just UA1, that's UA. This is just the length of the list. So this gives a functor from lists to abelian groups. So this means we can define a chain complex functor from S list delta to simplicial abelian groups just by this set. And then we have this category to positive chain complexes. So this we will consider as the chain complex, and then composing this with homology, we get homology of simplicial lists to graded abelian groups. So I will denote this by HX. So given a simplicial list, you get a graded abelian group, HX. Now, the thing is, let's say we have some augmented simplicial object with extra degeneracies. Then the homology of X is actually just isomorphic to its free abelian group generated by this X minus 1. And the corollary of this is that the homology of the associative operad is just 0. And then another corollary is the homology of the list nerve of the operad T alpha is just ZA0. Another corollary is this N T alpha is isomorphic to H U alpha, that where U alpha was, remember, the simplicial list, which goes to T alpha under T1. So what is the point here? The associative operads, well, has this operation which gives us the identity element. And basically, you can always put this identity element at the very end, and that gives you these extra degeneracies. Here, the idea is to send, I mean, if you have some simplex, just complete it all the way up to A0. And that gives you these extra degeneracies. So in each of these cases, you have extra degeneracies. Here, the idea is that when you consider T alpha, U alpha as a pair, this again has degeneracies by the degeneracies coming from T alpha, because everything lives in U alpha, they all disappear. Okay, so this is all I want to say. Thank you for listening.
So, questions or comments?
Oh, a
Yeah.
quick one.
Yeah.
Sorry. So you were rushing, you missed like a serious punchline, which is coherent nerves of things enriched in Kan complexes are quasi-operads.
Oh,
Because you did the
oh,
definition and you forgot
that's
there's
right. That's right.
yeah.
Thank you for reminding me.
Yeah,
So if
just
you have a Kan complex enriched operad, then this implies the coherent nerve of Q is a quasi-category. Yes, that's right. And this is a very important term, of course.
yeah. If this is not true, the
Right.
whole model is rubbish. Like
Right. Sorry.
Okay, thank
It
you.
was in my abstract, but I forgot to mention. Right. Thank you.
May I? About the category F that you see S list as a presheaf on that F.
Mm-hmm.
Is that category? I mean, is it does it have interesting properties? Like, for example, is it hybrid over
Which one
spec
are you talking
category?
about? F or
This
gamma?
F, this F.
F.
Yes.
Okay,
So
well,
how is it related with delta? Is it hybrid over delta
well,
or?
it's an existent result. Actually, as I said here, Reddy came up with all this F and this, but maybe he could have more.
Yeah, okay. So F is constructed combinatorially, but in abstract fashion. Yeah, we had these factorizations, etc. So we know, like, I don't have an explicit description, like you can think of an element F of this form. And the thing is that so the condition of being operatic really restrict what a simplicial list can be, and then we have this combinatorial description. Like for general simplicial lists, I have no idea. There is a relation with delta n. F has very nice properties, so I'm not sure about
Is it ready, for
exact.
example,
Sorry?
or is the ready category or generalized ready category?
The read structures, yes. Like
I think
they,
there is.
I mean, there is both F. I mean, it's not in the paper because we didn't use the read model structure.
Uh-huh.
But at some
But
point,
that was
yeah,
what I was planning to ask actually. This S list, for example,
yeah, S
does it
list.
have, does it
So
carry
S list,
a model
yes,
structure like simplicial set, uh, which
yeah. So at some point, so this didn't make it to the paper because it wasn't. I mean, we thought
Was
to use
already
it to prove.
very long.
Yeah, so the epsilon there has an F as well. The epsilon there has already structure. So you have all these results which are nice about homotopical limits, etc.
uh-huh.
We didn't use it, but it's very evident. Like if you look at the descriptions, etc., because you have faces degeneracies and things like that, which go up and down. You have all these very simple, yes.
And another, there was a to chain complexes. Uh, is it a part of an adjunction or is it just a functor?
Just a functor.
And there is no adjoint.
Mm.
There might be an adjoint from S to SAB, at least one side. Oh, so that the C, does it have a right or does it have a left adjoint?
I have to think
Uh,
about it.
so about that, so we are not the model is underdeveloped. I mean, it's just the first paper. But so if you look at dendroidal theory, for instance, they have um, model categories there which are equivalent to say connective spectra and things like that. Okay, so this homology and looking at these chain complexes is just like a first. Okay, what kind of homology comes to mind? This is it. So uh, uh, so this
Maybe.
is a question I just asked Özgün, like, can you
Okay.
come up with a homology? He said, okay, let me think.
Yeah.
Better
Well, but
maybe.
these
He's,
weights, I mean,
yeah,
these
but there
results
are
some other homologies that are already
yeah,
defined.
yeah, but there are deep connections between so deep homological connections which are fundamentally operatic. Could this model explain, or could this particular homology? I mean, it's still open. It's something to look to. I guess you can call it work in progress or
Yes.
something like that. Yeah.
Um, oh, by the way, I'm sorry. I thought that the functor is from not without tilde S list. Uh, so it is with tilde, right? This one. Yeah.
Yeah.
And maybe uh, one other question I was planning to ask. Why do you just take, why don't you just take monoids? Uh, not, I mean, uh, it will still work, I believe, but
Instead of
what
list, so
instead of
the,
list, yeah, just take monoids. I mean, just take
free
the,
monoids, not monoids, but free monoids.
no, I mean, not just, if you take monoids, then it will be complete, bicomplete, so it's complete, co-complete, so you don't have to bother with that finding.
Uh, big. I mean,
Everything
taking the
will be
monoids.
nicer that way. So your list
Oh no.
maybe have relations between
I mean,
instead of,
if you go, yeah, if you go to monoids,
yeah,
general monoids,
instead of lists.
yeah. So what will happen is you will have relations between lists, which you
Uh-huh.
don't really want in operative theory. They don't appear anywhere.
And
Oh,
So
they don't.
the list nerve is full faithful. So
yeah. So the thing is that
here you will have, I
yeah.
mean, if you take monoids, it won't be, I guess. Fully faithful.
Ah, okay, full, yeah, faith. Okay, I see.
Yeah, being fully faithful is something very important because
Okay, I see.
I mean the nerve theorem becomes really a recognition theorem for operands in simplicial lists. You don't get that. I mean, if you go to general monad, I guess you have to also specify that it hits free things, and why do that? Like, yeah.
And one more thing, do you allow infinite lists in that list or
No, no, finite lists.
finite? Oh, okay. So it's the lower tier of monoids.
Uh, Lower theories are way more general. This is just the monad. Like,
Okay.
I mean, we are not really
Up to a column.
using.
Column.
Yeah, there. Yeah. So it's just what
From
language
the
you
lower
decide
tier.
to use. I guess monads is a bit more inclusive. Lower theories are rather like
Finite
you
tier.
don't want. Yeah, lower theories are very uninteresting. So, uh, but yeah, I mean, so there is this monad actually. Um, Another thing is like if you change the monad, what happens? That's uh, so for instance, Leinster has notions of operads relative to a monad, and using these techniques, you can derive some type of nerves. And I mean,
Actually, lower
this
tiers
is
are
also a work in progress. So,
Also, one more maybe thing to add here is that, so notice we had this DN as listings, and that gives us operads. Now forget that condition and allow everything to be listings. Then these could be related to properads or props, things like this. So that's just one other
by the way,
possible
I believe that with
generalization.
lower tiers you're clear.
Mhm.
You have more.
I don't know. In a year, we will tell you more, I guess. And definitely proper.
Uh,
Uh,
maybe another question I want to ask was, I mean, did you ever check homotopy theories? Because there are some people interested in homotopy theory of operas. So maybe your approach
I
with
mean,
this,
yeah,
I mean, can it help you to build
no.
interesting
So
homotopy theories or
the
model categories? I mean,
yeah. So the point of the constructions is to model the homotopy theory of
oh, okay.
infinity. Like the coherent nerve. Uh,
But I
reg
mean, model categories
Yeah, yeah, yeah. So the
not
coherent nerve and its adjoint. Uh, this is also work in progress, right?
okay.
Kind of clear, but it should be equivalence once you put the gel model structure on simple. So there are tons of ways to do that. I don't know, like transferring Ciesinski model structure on the pre-sheaf. I mean, it's just a matter of finding what makes the technical stuff easier afterwards. But yeah, this will appear at some point. But yeah, the point is that this will be equivalence in the end.
Mhm.
Modulo, I don't know, unpleasant surprises, but I don't think so. And then you have a model for the homotopy theory of infinity operads, but also nice combinatorial constructions, which I mean will allow you to like do concrete constructions, etc. So in this direction, uh, up to the Cartesian model structure, I don't think there will be. So the real objective, actually, let me put it this way, is to have the Cartesian, co-Cartesian model structures, because the point of operas is to study algebras, and algebras are hard to study homotopy coherently. You really want vibrations. So those model structures should really be there. And then once you can study algebras with vibrations, you can really construct things very easily, like people doing quasi-category theory. This is really the point of the analogy. I mean, the reason quasi-categories are nice is because you have these combinatorial tools that you don't have, say, for, I don't know, like complete Siegel spaces and these other, I mean, there are tons of models, but I mean, theorems are provable in quasi-categories. So we hope to sort of facilitate, say, some constructions, etc., by having combinatorial methods to do that. So yeah, that's the work to be done.
Thanks. That's
Any
all
more
from
questions or comments? Melekna?
I'm sorry. I had a question. What are the advantages of higher categories compared to quasi categories?
So you mean like, what are the advantages of the quasi-category model with respect to other models? Is that your question? Or
The advantage of higher categories compared to quasi categories. Actually,
but
the other is advantages, more advantages. But I mean, is there any advantage of higher categories?
They are more intuitive.
so if I may, so your question, so the so higher categories, so quasi-categories is a way to do higher category theory, right? So when you're talking about quasi-categories, you are really talking about higher categories. So I don't know what you mean by when you say higher category.
I think what you mean is this simplicially enriched version.
Is that it?
Uh,
What do you mean by higher category? Yeah, could you?
okay, by higher category, I read something that higher categories are topologically enriched categories.
Okay, Özgün is right. Okay, so Özgün, you want to go or me?
No, I just said well, for me, the advantage is that they're more intuitive for me, at least.
So you mean the
Like,
topological categories are more intuitive or the quasi-categories?
no, topological for me.
Okay, so I've been trying to convert Özgün to quasi-categories over the past couple of years. So you shouldn't say that. Yeah, so the thing is the bedrock for building intuition is really, say, you start thinking about topological categories. Now the problem is when you start doing constructions with topological categories, it becomes a mess. Okay, so say try to study the definition of a homotopy coherent diagram or things like that. It's messy, like there are these big etc. Now, yeah. Now what happens when you go to quasi-categories and you go through coherent nerves usually, um, is that you do things there and everything is homotopy coherent automatically because you define things that way. And so say you want to talk about limits, colimits, or any other construction you may want, you just do it with quasi-categories. And you know things are homotopy coherent, number one. And number two is that the combinatorial methods which are available for quasi-categories, which is really Cartesian, co-Cartesian fibrations. So these are some big theorems Joel and Lurie proved. Really, you can perform constructions combinatorially and just say, oh, this model's my homotopy coherent functor this, or homotopy coherent functor that. Now, the second point, if you want to appreciate it, it begins with the Grothendieck construction for weak diagrams of categories themselves. Because checking the coherence laws can be really boring. Instead, you define a Grothendieck fibration very easily. And so even in two-category theory, I mean, you see the advantage of, say, using fibrations. And those tools are really only available in quasi-category theory. Some people have developed them for Siegel spaces. I personally don't like Siegel spaces, but anyway. And so the advantage is really statements that people knew were true or expected to be true you can write down combinatorial proofs. Are those proofs easy? Well, Lurie wrote 3,000 pages and it's ongoing with another 3,000. But are they doable? Yes. I mean, and in other models, you just can't. Sorry for the long answer, but yeah.
Thank you very much for the answers. These tools are, combinatorial tools are for, you talked about not about quasi categories, but higher categories have these combinatorial tools, right?
So the quasi-categories have the combinatorial tools. That's why it's the most successful model.
Combinatorial tools are for quasi
yes.
categories.
Yes. So pioneering work has been done by, it began with Boardman-Vogt, but you can look at Joyal's notes. It's a big book, or Lurie. But if you find these like introduction to quasi-categories and things like that, if they mention somewhat fibrations, as I said, you can to appreciate this point, I suggest looking first at the Grothendieck construction for categories.
Are there
Yeah.
little advantages of higher categories? Little. I asked about that actually.
Are there little?
There are some. Yeah, to understand.
I mean, okay, so the topologically enriched stuff, the thing with it is that they are observable. So for instance, say you're studying, I don't know, say you're studying some type of topological whatever. You can say, this is enriched in topological spaces. That the observability is what it is. Now, when you observe that, what you really want to do is take the coherent nerve of that topologically enriched thing and study that. That will be a quasi-category. You perform your constructions, and then you go back to your original intuition and say, look what I proved. I proved this result, but I used these combinatorial tools here. That's the practice of what really happens.
Okay, thank you very much.
Yeah, no,
Okay,
I'm
so
happy.
I think no more questions. My computer will explode. So this was the last talk of this year. We will meet next talk and see you later. Bye.
Yes.
Yeah, thank you very much.